Hello, and welcome to this session of Shadow the Scientist. My name is Jamika Marshall, and I am pleased to serve as the coordinator of the Shadow the Scientist initiative. The STS initiative is housed under the CREST, Creating Equity in STEAM umbrella of initiatives offered by a team at the University of California, Santa Cruz. I am so pleased to welcome all of you to our second session with the crew of the research vessel JOIDES Resolution. Today on this session, we will be guided by the onboard outreach officer, Aaron Anthony. And before we move to Aaron, I would like to acknowledge my CREST colleagues in the session today, starting with our Shadow the Scientist faculty sponsor at the University of California, Santa Cruz, and the STS founder, Raja Guharthakartha.
Hi, everyone. How are you? Elias, it's good to see you. Rich, it's good to see you. Erin, thank you so much for hosting us. I'm sorry I missed the previous session, but it's super exciting. This is our first foray into the world of paleoclimatology and oceanography, geology. So it's super exciting.
Fantastic. Thanks.
Thank you for doing this.
Thank you for that, Raja. And without further ado, we will turn it over to Aaron. Aaron, how are you?
I'm doing good. Excited to be back for a second session here. I'm going to show you around some of the same stuff. If you were here last time, you might see some similar things. I'll try to show you a couple new things, and then we'll have some new scientists at the end that are able to answer your questions. Some geochemists. We'll see their lab at the very end as well, but and I'll also be available for questions. So be sure to save those. And excited to get all your questions answered. So start out, I am on currently the JOIDES Resolution. As I said, I am the onboard outreach officer. So it's my job for this expedition, Expedition 401, to share all the research that we're doing out here right now in the Mediterranean. So we've now been out here for around 7 weeks. We've got 2 weeks left in our expedition. It is a long journey for us out here, but we're doing it all for science. And the big reason is we are taking cores of the ocean floor to study a number of things about Earth science. So looking at this map behind me, if I go up really close, you'll see there's a bunch of dots on the map here. These are all locations that over the past 50 years, we have taken cores of the ocean floor. And the reason we're doing that is to study a number of things. So it could be everything from the extinction of the dinosaurs to earthquakes to our past climate, which is what we're focused on for this expedition. So as I mentioned, we're Expedition 401. There's their mission patch up there. And we started up in Amsterdam back at the start of December, came along coast of Portugal, Spain. We sailed through the Gibraltar Strait, which is very exciting, and now ended up where we are now off the coast of Spain in the Alboran Sea in the Mediterranean. And the reason we're focused on this is we are drilling to get cores of rock that help us study something known as the Messinian salinity crisis. And this is a period where the Atlantic Ocean and the Mediterranean were cut off from each other. So in present day, we have this one connection, the Strait of Gibraltar. In the past, we actually had two, and with tectonic movement, that closed. And the Mediterranean basically became a big lake. And when this happened, it caused a huge amount of the water to evaporate, leaving behind a 1,500 meter thick layer of salt. So this had a huge impact on the ocean's climate, or the world's climate, the ocean's chemistry, and the ocean's circulation. And so we want to learn what the impacts of this were. And so by doing that, we can, in addition to learning about the past and the flow of this water, we can learn about the present, better understand this flow of water from the Mediterranean to the Atlantic, and refine our climate models, which help us prepare for the future and future potential extreme changes when there are things like changes in the ice caps and things like that. So we're really excited to be able to be out here studying this. We have about 30 scientists on board and 117 people on board. And today I'm going to show you around the ship so you can see some of the facilities where we're doing all of this work. We're going to start up at the bridge. We're going to go over and see the drill that allows us to take these massive cores. We're going to see the flow of where that goes into the labs. And then, like I said, we're going to do some questions. And we just had a quote core on deck a little bit ago. So there's a chance there's still some core actually flowing around out there. We will see. We get a core on deck every about 2 hours right now. So excited to show you all this. All right, to start, we're going to go outside. It is about a little bit later than it is in Hawaii and California. We are on GMT, so it's around 10 p.m. right now. So it'll be dark outside, but I might hit you a moon view on the water a little bit as well. So this is one of our watertight ship doors, which allows us for more extreme waves to be able to keep the water out. So, as I said, it is nighttime, so it is pretty dark out, but you can see we have a lovely view of the moon tonight, pretty clear. In front of me also here, you'll see some of our lifeboats. These can fit up to 70 people, as you see listed right here. There's 35 people assigned to them, though, so do boat drill, I'm sure that we know what lifeboat we're assigned to, know how to bring all our gear, how to get there. So in case of emergency, we can all be ready and safe. But you can see they are a little different than what I was expecting lifeboats to look like. It has like this bubble up here, which is actually where someone can sit and drive it around if you needed to in the water, which is pretty cool. And now I'm going to come around. We're going to the front of the ship, the bow of the ship, and I'll give you a view off of here. I think this is the one area you might see some waves and some clouds of the moon, and the front of our ship up here. And we're going to go ahead into the bridge where we're going to have a Frankie to show us around of how we actually drive the ship around.
And Erin, is it very cold out there?
It is not too bad right now. I wear this jacket because I got rained on once as a surprise, and I always want to be ready for that. It's been 50s, 60s most of the time. We've been here in the Mediterranean. In the North Atlantic, it was a little colder, but in here it's pretty good. And now we have Frankie here who's going to show us around a little bit and some of the tools in the bridge.
So guys, welcome on the bridge. So this is our bridge. It is like the front seat of the car for us. From here we navigate from side to side, from port to port, using our engine. This is our engine control, our telegraph. Let's push ahead and going ahead, pull back, and you're going astern. Okay, this is our steering wheel. We have 2 rudders on board, the back, 2 rudders, and then 2 propellers as well for the propellers. We have our autopilot. Once engaged and once we are doing, we have an autopilot. Just following the set heading that we are going to make it to the waypoint to waypoint. Here is our radar here. It can be ECDIS also, or electronic chart display. Here is our ship at the center now. And here are the other vessels on the green triangles here. Here you can see where it is going away from us. This is another vessel, which is called Delta Harmony. It is just only drifting around. As you can see this yellow thing here, this is the island, the land of Spain. You can see it there. You can see some good information here regarding the name of the ship, how far it is to us, what's its speed from us, the use of the AIS, or the automatic identification system. Okay, we used to call the other ships by the VHF, high frequency radios, and we have the MSF also, with the frequency. This is our echo sounder. If this is running, but now we cannot run it because it will affect the DP control. So you can see the bottom of the sea floor from our keel down to the sea floor with 2,000 meters. 2,000. Okay, it's just the light control.
Very cool.
Okay.
All right. Thank you so much.
Doing something from that.
Thank you so much. I appreciate it. Yes. And I'll mention one of the back rooms over here. We also have some of our thruster controls too. So we're not moving right now. We're trying to stay in one place. So we have 12 thrusters built to keep us in one spot as well. Thank you so much. Appreciate it. So one of the main goal of the ship is to be able to drill and take this ore out of the ground, which means we need to stay still most of the time. Although we need to be able to move around, which is how we drive. You know, if you have something that's going down thousands of meters to the seafloor, you want to make sure you're staying in close proximity so that that doesn't bend or move too much. So those thrusters is very important to be able to make sure that happens. And speaking of, in front of me, you will see the derrick. This allows us to be able to put our drill string, our tube that contains our drill, all the way down to the seafloor. So we are actively currently drilling. We are, not only is this going down to the seafloor right now, it is going over a kilometer underneath that. We are currently, I believe, at 1.2 kilometers, which we have just recently hit around 8 million years back in Earth's history in the rock that we are pulling up, which is around our age target. So we might actually stop drilling this hole in just a few hours and pivot to making another hole at this site to be able to get additional samples and help fill in some of the areas and gaps we might have had the first one. So what you'll see here is this yellow piece is known as the heave compensator. So when we have waves, this is able to move up and down and compensate and make sure that the drill can stay on the seafloor as we are going up and down on those waves. And the middle pipe is what the core is going up and down inside of. And at the very base of that is the drill. So we're going to go up close and take a look. It might get a little loud, so I might stop talking for a minute just so we can take a look at it. And as we go over, you'll see this is our caution line. That's why I'm wearing our safety gear here. And that's to make sure I can stay safe up close next to the heavy machinery. So let's go take a look at it. And this is around 200 feet tall above the water line, or the very important measurement, about 26 elephants tall. And now this tube is actually going down through the bottom of our ship. And I know it sounds like maybe not a great idea to put a hole in the bottom of the ship, but it's actually okay. The way the ship is designed, I like to describe it like an inner tube. If you've ever had an inner tube in a pool, there is a hole in the middle of that. It doesn't sink either, right? Well, the ship is like a big inner tube. And also it has it's called the moon pool, the hole. The whole of it is above the water line. So the water's down here, the whole of the ship is actually up here, which prevents the water from coming in. All right, let's walk down the steps so you can get another good view. So I'm even with the drill floor now, and when that tube of rock comes up, it will rest right here. And our technicians will pull a large plastic tube out of it, which looks like this. And this tube is around 10 meters long, which you can see, that's pretty long and probably kind of hard to manage if we wanted to try to bring that inside and work with that rock and observe it, which is why we put it on this table right here. We just had core come off of this, and it gets cut. So it gets divided in between each of these tables and segments with this tool here, which is able to put around and cut it, and then capped on either end. So the blue cap goes on the top because it goes towards the sky, and blue goes towards the sky. And then after it's cut, it goes inside of our labs here. We'll go in just a minute, but I want to give you a little peek here as well. We have some of our example drill bits sitting here, so and coring bits. This is what is actually on the bottom on the ocean floor. These are all flipped upside down. This is the part that actually goes and cuts into the rock. And you'll notice this red one is different than these silver ones in a big way. This one doesn't have a hole in the center. This is if you just want to make a hole in the ground. You're not going to be able to pull any rock up for our scientists to be able to study. If you want to get down to a certain depth fast, that's a great way to do it. However, these have holes in the center, and these are used for different types of drilling. So this one here is used for something known as piston coring. And out of this center, we'll basically shoot a 10-meter long tube or a big cookie cutter. And I like to describe it kind of like if you've ever put, a straw into a drink, put your finger on top and pulled it out. that's kind of like what we're doing with this rock. And that only works for our softer rock. When we get into harder rock, we actually need a rotary coring bit so that it can spin, we kind of carve into that rock and pull it out. And so this, there's one technique that can be used inside of this for rotary coring. When we get into the hardest type of rock, that's when we use this one, which you'll notice is a little bit of a different hole and distance for the cutting. The ship is currently off the coast of Spain. If it was daytime, you can actually see the coast of Spain over there. Our closest city is Marbella, Spain. And so we got here, I think like about 6 days ago now. So about a week ago now. And we will be here. This is our last site of our expedition. So we'll be here until we leave to go transit to Italy. And our last day of our expedition is February 9th. All right, so once we have that core and that rock, it goes inside the lab for our scientists to study with a number of different tools. So we'll go ahead in there and take a look. We got another one of our signature large ship doors here. So once these cores get inside, the first stop is going to be our machine right here, which labels them. This is actually a laser engraver. You'll notice we have a lovely laser-eyed cat up here that helps us with that. And you'll see this is the different names of our sites that we have. They're listed up here that can identify and be labeled onto cores. And then after they're labeled, they go over here onto this large rack to be able to either cool off or warm up, basically get to room temperature, because they can come up at different temperatures. You'll see they're also labeled with writing on the end of it. My thought question is, how heavy are the doors? I actually don't know exactly how heavy they are. They can get a lot of momentum though. So if you notice on them, there's specific spots to be able to put your hand to make sure that you're safe as you're opening and closing it. And so after they get to that room temperature, that's when they get to go to our scientists. So the first stop is our physical properties lab. And this is Jonathan, one of our physical properties specialists, who can show us around a little bit.
Right. So yeah, we're the physical properties lab. We're one of the first people anyway to get a real good look at the cores. Usually we scan this into it, but the tag's a little torn off. So
no worries.
Yeah, unfortunately.
All good.
But once we have it loaded in, I can tell it enter, and then this arm moves it down over here. This little laser, it actually measures how long the cores are exactly. So it double checks it from where they measure it outside to here. Then we measure 3 very important properties that are useful for figuring out like the different like properties of the core, because of like chemistry, etc. And that's density. It does that by shooting a gamma ray through it in order to figure out density. And then this is figures out the magnetics, how magnetic it is. And then this device over here, these 2 little hammers, they press down into it and send a sound wave through it, so we can figure out how sound travels through the core. That helps us correlate what we have in the core to what we call the seismic surveys. These kind of like the way we kind of visualize what's going underneath before we actually come drill it out. And then we have these one of the last measures doing thermal conductivity, which is just how well heat passes through it. And then the final one is actually the first one that we actually measure. We actually have a sample in there right now. Natural gamma radiation. This one actually measures as the name says, the natural radioactivity generated by the core. And all these properties are really really important for helping us correlate between different sites, between different holes in the same site, figuring out different types of rock types, and later on figuring out maybe like changes in climate and environment, the sources that are coming in for the rock. Yeah, all very, very important stuff, really, really cool stuff. But when we're done with all these measurements, we take the core, we place it back over here on the core rack, which Aaron already showed you, and then it goes straight to the splitting room. Yeah.
Fantastic. Thank you so much, Jonathan.
Anytime.
And we'll go over to the splitting room next. So in here, I'll open our magic doors. Ta-da. And you'll see we have one of the cores that's sitting here right now waiting to be split. And so there's 2 different ways that we can split these cores in half. One is over on this side. It has a wire that can be strung across here. It almost works like a cheese cutting wire, if you've ever seen those before. And it can go straight along the whole thing and cut it. Again, we get some harder rock. And once that happens, which is what we're using now, we have a saw over here that can actually run down it and cut it in half. When we cut it, it's going to be cut along one of these blue lines on the tube. Those are the guidelines for that. And so now, why do we want to cut these cores in half? Well, we've observed them in their full form, and now we have some different things to be able to do now that they are cut in half. You can see them better. So one path they take is over here, and they can go onto the working table and work the working half of the core where samples are actually taken of it. You'll see there's a little flag here of a sample to be taken. And then on the other table is our archive half. And these are the half that are not sampled. They're kept in this form, and they are observed and scanned by our sedimentologists. I'll give you a close-up look at some of the more recent rock that we've pulled out of the ground. And so they're looking at the different colors, small trace fossils, things inside of this. And they're also looking at close-up pictures of it, which are taken via this camera here that can actually slide down the full length of it. We have another tool over here, and hi, that's Simon back there. Our schmizzle. Do you want to talk about the schmizzle for a minute and what it does?
Yeah.
Sure.
Hi there. So this is the section half multi-sensor logger, which we put the half core on the track, and this machine runs along it at a pretty slow rate, and it measures the reflectance at different wavelengths, and it measures the magnetic susceptibility, which is a property of the rocks to do with magnetism.
Very cool. Thanks so much. Yeah, appreciate it. And so after they get analyzed, reported, and described by this team, then one of the other things we really care about is the age of the rock. So you'll see we have another core that is lined up here to go inside. And this is our paleomagnetists who manage this, who are largely looking at the magnetism that they're able to detect within these cores. So, within Earth history, Earth's magnetic poles have actually switched directions. So your compass, if you were holding it, it wouldn't have always pointed north in the same direction that you would think of now. And by looking at when we see those reversals in that core, we can determine how far back in history it's gone because we know when the reversals occurred. Our other team that's able to look at the age is our micropaleontologists over here who are all looking through their microscopes. So they're looking at fossils, but not the type of fossils you might think of when you think of dinosaurs or things you see in a museum. These are tiny, tiny, tiny fossils you can only see under a microscope. And by looking at these, we know when these different tiny organisms began to exist and when they became extinct. And so when we look at these different groups of microorganisms, we can get an idea of the age of the rock. And this is really important because as we're going down, we have certain target ages that we're looking for, that 5 to 8 million year range. So these are the teams that are really important to tell us we've gotten to where we need to. We've drilled as much as we need to. And I'm currently in their wet lab, which is where they also prepare their samples to be able to go under the microscope. So we have sink over here where they're actually manually washed off. We have over here oven where they are then dried off after they've had the different residues and things that are washed away. We actually have one sample that's being agitated over here right now on our lovely shaker table. And we also have a spot over here where we're able to make slides to be able to put at the microscope. So we have a UV light and curing. You'll see we have a couple slides here. They don't look like there's much there, but that's why we need a microscope to be able to detect them like that. So the team recently thinks we got to around that 8 million year mark, which is super exciting. And we have a crossover at midnight. So you said it's like 10:20 here now. And when that team gets here, so we switch every 12 hours. We do run 24 hours a day. So I have a counterpart who will take over for me at that midnight time. They'll confer and make sure we're good to stop drilling here and then go on to another hole. Now we have one more lab to go visit downstairs. And then we'll have an opportunity for questions to our geochemists who are the ones in that lab downstairs. And as we go there, I'll be passing through our staircase, which you'll see we have some very signature decor in our staircase. First of all, here is our pet wall. So these are the pets of all the scientists and technicians on board. We are, again, out here for 2 straight months without going to shore. So this is just kind of a nice reminder and memory of home whenever we're walking the staircase. These are my cats, Eddie and Olive. You'll see some people took a joke out of it too. These are apparently about elephants. And then also on the walls, you'll see a bunch of patches and logos. These are the logos of past expeditions. And, I mentioned we're expedition 401. So there have been a lot that have come before us. We even have some logos from the ship that came before us, the Glomar Challenger, This ship has been working since the 80s, and that ship is what preceded us. And you'll see these logos continue to go down even further. I'll take a quick peek down on one more floor for y'all in the mess hall so you can see where we eat, and then we'll pop over into the geochem lab. So we do on each shift have snack breaks, cookie breaks, the very popular ice cream machine. Then we have some yogurts, juices, milks, soda, and of course a very important confections bakery, salad bar over here. And then when it is time for meals, they are served out of here. And I'll give you a little preview of what is on the menu for dinner. Or this is what we actually had earlier, because I had a big pot there. So, so I had a question. How often does the ship get resupplied? So during these 2 months, there are no resupplies. It's just when we go into port in between expeditions. So during our entire expedition, we had to carry everything with us that we needed. So as we get near the end, there's less, fresh fruits and vegetables and that sort of thing. But we have more, pastas and fish, that sort of stuff. All right, so we're gonna head over to the geochem lab now and see what they're up to. Hi, Melissa. Hi. So we're now in the geochem lab, and first I'll show you, or do you want to talk about the okay, so we have a couple things going over here right now. We have samples that are put into these presses, and you'll see these are actually being pressed down and squeezing out water from the rock samples that we pull. And so these syringes right here are collecting that water. And we're able to study what we detect in that. So we put that water into a variety of tools over here that are looking at everything from alkalinity, salinity, pH, and really help detect and give extra clues about the rock and different things that are occurring at the time when the sediment was deposited on the ocean floor. Why are so many people working so late at night? So we work 24 hours a day. So no matter what time it is, it's around the same number of people that are actually working on the ship. So we either usually have 6 to 6 shifts or 12 to 12 shifts. So I'm on 12 to 12 right now. So I'll still be working until midnight. And Melissa, do you want to show us what you do on your side of the lab?
So one of the jobs that the organic geochemist has on board, and I'm the organic geochemist for the ship, is to measure, I don't think we have any pretty samples anymore. We take a bit of the mud as it comes up on deck, when they go on deck, and immediately put it into a low temperature oven to warm it up and drive gas from the sediment into the headspace, the open part of the vial. We then can use a syringe to pierce that opening, lock that gas inside, and then put it into the gas chromatograph here. Be able to say something about the abundance and the type of gas that's in that sediment, with the understanding that we want it to be a certain mix of gas or not a certain mix of gas for safety reasons. And so far, everything looks good. And here we have a balance, which on land, would not be a part of a tour. But here, a big part of our job as the organic geochemist is actually to weigh out sediment samples to figure out their calcium carbonate abundance. And that's actually what I'm doing here. So the balance tells us, right, the weight of the sediments. Then we can come here and actually use the coulometer, which basically exposes those sediments to acid, captures the gas that's generated, and actually gets at this calcium carbonate percentage. So it's actively calculating that from the sediment that's in there. And so soon we'll know how much that calcium carbonate is in that sediment.
It's very cool. I think you had a question, which was, what does the gas tell you?
Yeah, so it tells us a couple of things. So the people who study the gas generation have learned that, different ways that gas is formed. So microbial generation, or kind of deep earth processes generation, and also kind of the abundance and the type of that gas would tell us then about what's generating that gas. Here we mostly use it, we archive all that data so someone can go back and look and try and piece stories together about that generation and what's making the gas. And here we're using it to be able to drill deep into these units to not hit pockets of gas like they would an industry be interested in hitting, because we're actually not equipped as a vessel to withstand the pressure of actually hitting a huge gas bucket. So we take the sediment, we generate the gas off the sediment, and then see what it looks like.
Cool. I think you got a follow up. What specific data does the abundance of calcium carbonate provide?
Yeah, so each of the sediment samples, so we take a sediment sample, we would grind it up to a very, very fine powder. Inside each of the sediment samples, right, is a mixture of different components, things, mineralogical components and small sea creatures, right, things like foraminifera, single-celled protists, which are made of calcium carbonate. And so the varying abundance of those tiny sea creatures made of calcium carbonate versus the mineralogical component tells us, back through time, the variations of those different components kind of tell us about different things going on in the climate, and also those basically the trends, the comings and goings of amounts of calcium carbonate, CaCO3, can then tell people where to focus on if they're really interested in those sorts of units.
I got you. Very cool. All right. Well, thanks so much. Do you need to finish this measurement?
Yeah, I'll finish
okay.
this one and join you in a second.
All right. So Melissa's going to be with us in a minute to answer some questions. So think about those, and then we'll go chat for a minute and answer some questions in the meantime. See you in a bit. All right. Well, thank you all for joining us for the tour. And yes, now we have some time for questions. So I'm going to go head into our conference room, set up in here, and then after Melissa finishes that measurement, she will join us too. And if you'll notice, we'll also have still some decorations up. We were out here for Christmas and New Year's. We still have our 2024 banner out here, and we had a talent show for New Year's. So this was the banner for the talent show. All right. Up. Right. While we wait for Melissa, I can take some. I see we have some in the chat. Let me take a look. What happens to the core samples when analyzing is complete? Great question. So it depends on what ocean you were in, where the samples were taken. So for us, since the samples were taken in the Atlantic, they are going to something known as a core repository in Bremen, Germany. And this is where all there, plus College Station, Texas, and Japan, are all the cores that have ever been taken on expeditions like this are stored for future use. So this is not the end of the life for these cores on the ship. If anything, it's just the very, very, very beginning. So not only are these scientists that are on board right now going to study these for many years to come, any scientists who are interested can also request to be able to look at these samples, analyze these samples, and make it a part of their research. So the hope is that this will inform a lot of future research on the exchange of water between the Atlantic and the Mediterranean, past climate, and the Messinian salinity crisis. All right. What is the reason for being off the coast of Spain? So at this location, this is our one site in the Mediterranean for this expedition. And we are really looking at those, as we said, those former gateways between the Atlantic and the Mediterranean. And this was a crucial place of water exchange in the past between the Atlantic and Mediterranean. So by drilling down here, we're able to get samples of that current and that water flow without hitting a huge amount of salt, because it's very hard to drill into straight salt. So we're drilling kind of right outside that in a safe area that was approved, where we thought we can get the best data on these currents and sediment deposits. And sorry if I keep turning my head, the chat goes up sideways on my phone when I go to look at it. Oh, we got Melissa coming. I'll wait to save those for her. No, you're all good. We'll let you get settled for a moment. Melissa's back. Hello. Well, first, I was just talking about why we picked specifically here in the Mediterranean, and I mentioned we didn't want to hit a huge amount of salt and things. They were talking about why is it so so the question is, why is it so challenging to drill through salt?
Yeah, it's both challenging because it doesn't want to go into the barrel, and also because salt, I mean, so you're looking for one, because that's not the units we want to study, two, because it's hard to drill through and keep it in the core barrel, and three, because it can form a trap for gases and things like that. So yeah.
All right, keep doing this. How do you replace or repair parts during the expedition?
So I will also send you to a really great blog post that's about 3D printing on board, and so they can 3D print parts.
You can talk about. I'll go grab my part.
Yeah, so they can 3D print parts. Also, there's someone on board who can fix virtually everything. It's actually quite amazing. I mean, I think there's definitely been expeditions where there are things they couldn't fix, really big things, and then have to go back to port. But I think a surprising number of things they either have spare parts for, or they can print, or they can fix. So for instance, the balance I just showed you was down for half a day, and they were actually able to, Yuri on board was able to fix it and get it back to us. So
this, you might recognize, you saw on the catwalk some of our drill bits. This is a 3D printed version of the drill bit. You can actually see it in the right orientation, because this is the way it's actually going down into the ground. So this was printed on the printer on board. Cool. All right. Why do you test on the ship and not on the ground? Does it have to be right away?
Yeah, I mean, so it's a great question. Some of the things that we test for now help us and kind of inform future sampling. So knowing the answer now is really valuable. And we're kind of figuring out if you want, if we're figuring things out on the fly, and actually having science meetings now where we talk about our findings already. So people are kind of figuring out their science. This is my lab mate, Erica, the inorganic geochemist on board. And so and now I blame completely. Oh, and some things actually change, right? So we have to do the gas content right away. Some of the things we need to know about to inform future decisions, and some things like the physical description of the cores, the colors actually change right away. And so getting people to describe them the minute they're open is actually quite critical. So all those images and things we will use for years and years to come, and having people go and look through them actually really helps later. So them being fresh is actually critical.
How does Earth's magnetic field flip, and can it be predicted when it will flip again?
Do they have predictions?
No, they don't.
I was like, I don't think they can do that. Although the movie The Core would maybe say otherwise.
We all watched the movie The Core on board, so we all very much enjoyed that.
Yeah, and so I don't know about
it's not fully understood.
Right.
We know that it has happened. We don't necessarily know why, and I can only answer this so confidently because I asked our paleomagnetist this exact question a couple of weeks ago. So.
I was like, like this and a little bit of this. No, I really don't know.
Yeah. How old is the most ancient core this expedition has discovered?
We are targeting 5 million years ago to 8 million years ago.
Yeah, so I think, did we get?
I think we went to 10 in one of the holes, though.
Yeah, they'll refine the age model, but we think based on the biostratigraphy done on board, the organisms that tell us about different units, we think 10 million, roundish.
Yeah. After things get fixed on the fly, do you go back and refix them, or the plastic fix is permanent?
That's a good question. I mean, I think they don't, if it's critical, right, like drill and that sort of thing, it's definitely not fixed with the plastic. So like they have the metal, what do you call those blocks that they then carve out of?
Stock.
Yeah, stock blocks. If it's like a part, like a small part, and then anything kind of really significant like drill bits, they just have a room full of them. So the goal is to they're not 3D printing like something that critical, like a drill pipe or drill bit. Come join.
Yeah. I do know. I was just talking to Yuri the other day, though. They do have some parts they've 3D printed, and they have stayed 3D printed because they also still work. We have a new guest joining us. You want to introduce yourself real quick?
My name is Oscar Cavazos. I'm one of the geochemistry technicians on board the JR. I work with Melissa and Erica.
Yeah, we're representing full force here from the Geochem lab.
Yes, I think we got one question for you, Erica, which was yes. what is the main focus of the inorganic geochemists on board?
I'm working for measuring the water in the maps. We measure the water samples to get the information on what kind of experience water did under the sea floor.
All right. Who finances this expedition?
So all of the countries that are part of IODP, so all they call them IODP member countries, basically their science divisions of their government. So in our case, in the US's case, National Science Foundation, the tiny amount of budget that goes to science in all of the US has a tiny amount of their budget that goes to fund drilling here. And so each of the countries represented kind of pays into the system and gets a certain number of their scientists sailing each expedition. And so because of that, we have a really nice balance of scientists from all over, and all of those countries represented paid into this system.
All right, perfect timing. Ready to come back. One of the properties being measured is magnetism. Why is this important?
The Earth's magnetic fields, right? That question. I mean, I guess I don't know how much you talked about earlier.
Yeah, you can go ahead and say it again.
So yeah, the changes in the Earth's magnetic field can tell us something about the timing of the intervals that we're in, and so it's a good chronometer, like another marker of time that we can use. Those changes between normal and reverse polarity that we talked about, that we nor no one understands how these changes happen or why, but we have a really good understanding of when. So
how can paleoclimate research help us prepare to adapt to climate change impact?
Yeah.
Mediterranean Sea has a high salinity water, and it's a very high density. So it flows through the Atlantic water, and it drives the ocean currents throughout the Earth. So if the balance of salinity and temperature change, it may change the Earth climate. So it's important to understand what kind of change will happen in the future.
Yeah. I mean, so what I didn't really the sensitivity of all of Earth's climate to flowing water, so all of the water in the ocean kind of moving around in a pathway that we know fairly well, though there's still things to learn, that pathway has changed through time, and all of those changes changed our climate. And so we try and understand how those pathways change with salinity and density, like Erica talked about, and other variables, because we're really curious about how that would drive climate in the future.
Can you each speak briefly about your education background and how you became to be a part of the JR crew?
Yeah.
Go down the line?
Yeah. So I did a small liberal arts undergraduate, I did a master's degree, I did a PhD, I worked for the USGS for a few years in there, and a postdoc, and now I'm at the University of Notre Dame. I got staffed on the JR as an organic geochemist because I saw the announcement of this cruise and the kind of research that they were interested in, and I proposed to link it to the kind of research that I do, studying changes in precipitation on land and how those are influenced by the ocean currents nearby. And so I was staffed after a proposal. All the scientists are staffed after they write a proposal and are chosen based on that work.
I was raised pretty close to the Gulf Coast, so a lot of time was spent on the beach, seeing the coastal sort of processes. So that influenced me to go to the university at Texas A&M in Galveston to study environmental science, but mainly coastal sedimentary processes. Graduated, and I went a different route. I went more IT route with GIS stuff. I was there for about 9 months. Didn't really love it. and I missed the geoscience aspect of what was mainly my undergrad. So I saw this position open and I went for it. Here I am today, JR.
I was born in a small town in front of the Pacific, and I also enjoy the beach life in my childhood. And my background is actually engineering. So I was the undergraduate to graduate school, but I used the IODP samples for my papers. So I wanted to know more about the paleoclimate. So I decided to come here again.
I also have an engineering background, mechanical engineering, but I always liked to kind of be the translator between the technical things and the public. So with my career, I went to MIT and NASA and kind of served different roles there as that translator. But I left my role at NASA this past year and was looking for opportunities to do things you couldn't really do if you were working in a full-time job like that. So I applied and went through a number of interviews and got accepted. So yeah, I'm here with one other fellow outreach officer as well, who does very different stuff than me, does really incredible art, while I do like social media and video and things like that. And we're a good complement to each other. All right, I think we have time for maybe one more question. So I think there's 3 here. I'll scan it real quick. Are there opportunities for high school students aboard the JR? So I'll say real quick, the one student opportunity, I think there's one more of them left, is the School of Rock, which is where students are able to sail on transits. So when the JR is going from the start point or the end point of one expedition to the start point of another, and students are able to ride on it during that time. So I think that would be the best one. Is there any others you want to mention? Thanks. Okay. All right. I think that's probably all the time we have. So thank you all very much. Super appreciate it. And I think we have one more of these Shadow the Scientist tours left. So hopefully we're able to get you some other great guests then as well. So thank you everyone for tuning in.
Have a good rest of your evening. Aloha.
Aloha.